Pluto, a remote and cryptic world, was once a lone and dependable planet in our planetary group. However, late discussions among leading astrophysicists, including Neil deGrasse Tyson and Michio Kaku, have pushed Pluto back into the spotlight with astonishing discoveries. These researchers have suggested that Pluto's orbit may ultimately intersect with Neptune's, an idea that raises questions about how such an impact could happen and what the consequences of such an enormous event could be. Could this lead to a fascinating and rare phenomenon, or is there more to this potential planetary collision? Join us as we explore the possible outcomes of a Pluto-Neptune encounter. Pluto, once viewed as a planet in its own right, is now relegated to a smaller category due to its unusual orbit and its status as a dwarf planet. Despite its demotion, Pluto remains a subject of interest and research within the scientific community. Recent examinations by leading cosmologists suggest that Pluto's orbit is dangerously close to Neptune's, raising alarms among astrophysicists like Tyson and Kaku about the possibility of a catastrophic collision between the two. But how could such a crash happen? Unlike other planets in our solar system, Pluto follows an eccentric path around the Sun, taking an astounding 248 years to complete one full orbit. Since its discovery in 1930, Pluto has not yet completed a single orbit around the Sun. However, the intrigue surrounding Pluto doesn't end there. Its orbit is characterized by a highly elliptical shape, unlike the nearly circular orbits of larger planets. What makes Pluto's orbit even more puzzling is its tilt. Pluto's orbit is inclined at an angle of 17 degrees to the plane of the solar system, adding complexity to its orbital dynamics. This tilt, combined with its irregular shape, makes Pluto's orbit significantly more chaotic compared to other planets. One of the most fascinating aspects of Pluto's orbit is its interaction with Neptune's orbit. For approximately 20 years of each orbit, Pluto actually comes closer to the Sun than Neptune, a surprising fact given their positions within the solar system. This raises the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets in the solar system. When Pluto's orbit was first studied after its discovery, astronomers sought to understand its peculiar trajectory. Unlike the orbits of other planets, which lie close to the ecliptic plane, Pluto's orbit stands out due to its steep inclination and elliptical shape. The mystery deepened when it was observed that Pluto's orbit does, in fact, cross Neptune's. This apparent anomaly is resolved by the complex gravitational dynamics of the solar system, specifically through a phenomenon known as the three-body problem. The three-body problem in astronomy refers to the challenge of predicting the motion of three objects, such as Pluto, Neptune, and the Sun, that influence one another through their gravitational forces. The interactions between these objects create a dynamic system that is difficult to predict, as each body affects the others in a constantly changing way. For Pluto, this three-body problem explains why its orbit is stable despite crossing Neptune's. One key concept that keeps Pluto's orbit stable is libration. In the case of Pluto and Neptune, libration refers to the phenomenon where, whenever Pluto crosses Neptune's orbit, the two planets are always at least 90 degrees apart. This spatial separation is crucial in preventing the two bodies from colliding. Another significant factor is vertical libration, which refers to the upward movement of a celestial body within its orbit. For Pluto, this means that when it comes near Neptune or any other large planet, it remains positioned well above or below the plane of their orbits, adding another layer of protection against potential collisions. A third concept that stabilizes Pluto's orbit is VZK wobbling, named after the three scientists, VA, KL, and O, who studied the motion of celestial bodies. This phenomenon refers to how Pluto, Neptune, and the Sun influence one another through gravity, causing slight changes in their positions over time. In Pluto's case, VZK wobbling explains why its orbit, despite appearing erratic, remains stable. These forces contribute to maintaining Pluto's orbit over extraordinarily long periods, perhaps even billions of years. Although Pluto's orbit is chaotic by nature, these gravitational effects from other planets help keep its trajectory stable within the broader context of the solar system. These forces play a vital role in preventing planets and other celestial bodies from colliding, ensuring the stability of our planetary neighborhood. For Pluto, this stability is particularly significant, given the ongoing discussions about a potential collision with Neptune. Understanding Pluto's orbit provides insight into the dynamic nature of the solar system and serves as a reminder that even the most seemingly unstable orbits can achieve a state of balance through the complex interplay of gravitational forces and orbital mechanics. The study of Pluto's orbit also highlights the need for constant research and observation to better understand the forces that shape our solar system. Pluto's case illustrates the importance of studying the unusual behavior of celestial bodies and the role that gravitational interactions play in their movements. The concept of orbital resonance, which refers to the delicate balance of gravitational forces that govern the orbits of celestial bodies, is clearly demonstrated by Pluto. Even small changes in its position or velocity can significantly alter its long-term orbit. In the late 1980s, virtual simulations provided valuable insights into Pluto's orbit. These simulations showed that, despite the stabilizing effects of phenomena like libration, Pluto's orbit can still be highly unpredictable. A tiny deviation in its initial conditions, such as its position or velocity, could result in dramatic differences in its path over millions of years. However, these models also demonstrated that Pluto's orbit remains relatively stable over billions of years, suggesting that its journey around the Sun follows a subtle order. Even if it appears chaotic, however, these simulations also revealed the challenges of making precise long-term predictions. The three-body problem, combined with the sensitivity of the system to initial conditions, makes forecasting Pluto's future trajectory a complex and uncertain task. While simulations are valuable tools for understanding and predicting the behavior of celestial bodies, they are limited by the precision of the initial data and the complexity of the forces at play. These challenges are amplified by the fact that eccentric orbits like Pluto's tend to be turbulent and difficult to predict. The case of Pluto's orbit serves as a reminder of the ever-changing and dynamic nature of the universe. While we have made significant strides in understanding space, Pluto's example shows just how much we still need to learn about the gravitational forces shaping our solar system. The gravitational effects of the giant planets, such as Jupiter, Neptune, and Saturn, play a crucial role in shaping Pluto's orbit. Their positions and gravitational influences have profound implications for the stability and trajectory of other bodies in the solar system. This brings us to the question: why are prominent astrophysicists, like Neil deGrasse Tyson, raising concerns about a potential collision between Pluto and Neptune despite the intricate forces working to prevent such a scenario? Tyson, a renowned astrophysicist who played a significant role in Pluto's reclassification from a planet to a dwarf planet, offers a thoughtful perspective on the evolving nature of celestial mechanics. He argues that while Pluto's orbit is stable for now, it may undergo significant changes in the future. This possibility highlights how much more we still need to discover about the forces that govern our solar system. Tyson's views on Pluto's reclassification and its current status as a dwarf planet are rooted in the ever-expanding understanding of our solar system. He believes that this reclassification is not a demotion but rather a necessary adjustment to our growing knowledge of the diverse bodies orbiting our Sun. His approach to celestial mechanics emphasizes ongoing learning and adaptation. Tyson acknowledges the complexities of Pluto's orbit and its interactions with Neptune while recognizing the inherent unpredictability of space. He suggests that while Pluto's orbit has remained stable for billions of years, there is always the possibility of unforeseen changes. As we learn more about the forces acting on these distant bodies, new discoveries may challenge our current understanding. The complexity of Pluto's relationship with Neptune is an extraordinary example of how even well-understood orbital dynamics can be subject to future revisions as our knowledge advances. Moreover, Tyson's observations about Pluto's orbital resonance with Neptune, where Pluto completes 2 orbits for every 3 of Neptune's, demonstrate how delicate and finely tuned the mechanics of the solar system are. This resonance maintains Pluto's stability by preventing it from coming into close proximity with Neptune, a critical factor in the continued stability of both celestial bodies. In conclusion, Pluto's orbit serves as a fascinating case study in the intricate and dynamic nature of the solar system. It exemplifies the delicate balance of gravitational forces that govern the movement of celestial bodies, as well as the ongoing need for scientific exploration and discovery. Whether or not Pluto and Neptune will ever collide remains a topic of speculation, but what is certain is that Pluto continues to capture the imagination of scientists and the public alike. The possibility of a collision between Pluto and Neptune, while unlikely, sparks curiosity about the long-term dynamics of the solar system. Astrophysicists stress that understanding such interactions requires not only complex modeling but also an acknowledgement of the limitations of our current tools and theories. As technology advances, simulations and observations will become more accurate, allowing for deeper insights into Pluto's trajectory and its relationship with Neptune. The study of Pluto also underscores the importance of re-examining celestial mechanics. Its orbital resonance with Neptune, coupled with stabilizing factors like libration, VZK wobbling, and vertical displacement, demonstrates how chaos can coexist with stability over astronomical timescales. These phenomena remind us that even the smallest celestial bodies, like Pluto, are influenced by the larger forces shaping the solar system. Michio Kaku, another leading astrophysicist, has also shared insights on Pluto's unique position in the cosmos. He emphasizes that while Pluto's current orbit appears stable, subtle changes in the gravitational influences of larger planets or external forces, such as passing stars or rogue celestial objects, could alter its orbit over millions or billions of years. Such changes could potentially bring Pluto into closer proximity with Neptune or other bodies, increasing the risk of interaction. Kaku also highlights the importance of studying Pluto not just as a dwarf planet, but as a window into the early solar system. Its icy composition, unusual orbit, and distance from the Sun make it a key subject for understanding how the solar system formed and evolved. Recent missions, such as NASA's New Horizons spacecraft, have provided unprecedented data about Pluto, revealing it to be a dynamic world with an active surface, cryovolcanoes, and a tenuous atmosphere. The renewed interest in Pluto has also sparked debates about its classification. Tyson's role in its demotion from planet to dwarf planet has been both praised and criticized, sparking public discussions about what defines a planet. While Pluto no longer meets the criteria established by the International Astronomical Union, IAU, in 2006, its unique characteristics and scientific importance ensure it remains a focal point of planetary science. As research continues, the question of Pluto's potential collision with Neptune remains a theoretical exercise rather than an imminent threat. However, such discussions are vital for expanding our understanding of orbital mechanics and the forces that govern the movement of celestial bodies. They also serve as a reminder of the fragility and complexity of the solar system, where even minor changes can have cascading effects over vast timescales. Ultimately, Pluto's story is one of discovery, debate, and intrigue. From its reclassification to its dynamic relationship with Neptune, Pluto challenges our assumptions about the cosmos. It reminds us that the universe is a place of constant change, where even seemingly stable systems are shaped by unseen forces and subtle interactions. The continued exploration of Pluto and its orbit will undoubtedly yield new insights, further enriching our understanding of the solar system and our place within it.